All right, these are the notes for solving exponential and log equations all different ways. So the warm-up is to sort the equations. You're not solving them, just sort them into 4 different categories. Exponential equations that you can find the same base, exponential equations that you cannot find the same base, logarithms that have the same base, and log equations that do not have the same base. So the first one here, and on the Desmos activity, you're just going to drag the equations and match them up in the right place, so into 4 different categories. But here, if you have a hard copy of the notes, I'm going to write these in the boxes here. So the first one goes here. They both have the same base of 5, so log base 5 of x plus 2 equals log base 5 of 4x minus 7. The next one, you could get this in the same base here because 49 is 7 squared. So if you put this in the other place, I can understand it, because in other words, log base 7 of 7 squared equals x. And then x would equal 2 there, but we'll talk about that later. This one, you can get this in the same base. 3 to the x equals 3 cubed, because 27 is 3 cubed. But if you happen to put that down there, I can understand that. But the next one, 7 is the same base, so you can put that one here. And the next one, it doesn't have the same base. So when there's no base, there's no base there, it's 10, so this goes here. This one, not the same base, so this one has the same base. It's a logarithm, goes here. And e to the x plus 1 equal 10, not the same base. It's exponential. Log base 2 of x equal 1. So I'm going to put that one here, but you could make 1 2 to the 0. No, that one goes here. And then this one is not the same base. So 4 to the 2x plus 10 equal 26. This one is the same base. I'm not going to try to squeeze that one in there, but it goes here. And then this one does not have the same base. So the objective for this lesson, students will be able to solve for the missing variable in the exponential equation on log algebraically and with technology when there are different bases. So we're going to take notes. You can take them on a hard copy, or Well, you can take them on the hard copy after class. During class, I'd like to use the Desmos slides, and then we're going to do some practice, extra practice on the slides or on Desmos. So we talked about this, the natural log, a little bit on that turkey activity. There was a problem with the natural log, or it was an Euler to an exponent. So E is the natural log. E is the natural base or the Euler number. E is an irrational number. It never ends or repeats. So some of the digits here, 2.71828 is what I always used when I was in high school, but then it continues on. It's like like pi. Pi is an irrational number. You can find E as a button on your calculator. E lets you model continuous growth, so it can be very helpful in real world problems, which we'll do the second day this week, Thursday or Friday. This is important because when we use E with logarithm, the log base E of x is called the natural log and is written natural log of x. So the next slide. This is putting a graphic organizer that you might want to use when you're solving equations. So you have the same base exponential. What you want to do is equate. The pen just messed up. Let's see if I can reset it here. Let me reset it. All right, so same base, exponential. You want to equate the exponents. And solve for x. Logarithm, if it has the same base, equate the expressions. After the word log, and then solve for x. So if you can't get the base the same in an exponential, you want to isolate the exponential. Switch the equation to the equivalent log form. And solve for x. And you'll see what this means in a second here when we do some examples for the logarithm. And switch the equation to its equivalent. Exponential form. And then solve for x. Whoops, skip the slide here. So when we don't have the same base, you create a y table that stands for original inverse. The do and undo table, we can do it that way. And then you're going to solve using inverse operations. And then you can use a calculator if you want to get the decimal equivalent. That's what that means here. So you don't have to evaluate. If I say find the exact answer, then you wouldn't use the calculator in step 3. But let's go over some examples. And I think by doing that, it will clue you into what I mean. So how do we solve when we can't get the same base here? So what I said is to isolate this exponential. So the first thing you're going to do here is divide by 4. You have 10 to the x minus 7 equals 2. And now since this is base 10, you're going to change this to the equivalent log form. So you got log base 10 of 2 equals x minus 7. So this is in this form, base exponent number, and you want to change it to this form. So base, so log base So let me write that a little bit better so the subscript is not so big. So you're changing it to the equivalent log form. So base, don't confuse this with the Euler number. So base exponent number equals log base number exponent. This is a b. So here's the base exponent number. So now we want to get x by itself. So you have to add 7. So you would put this on the calculator then and give the decimal approximation. So let me see if I can get a calculator here to show you. So if you go to Desmos and the graphing calculator, and so I want log base 10 of 2 plus 7. So I couldn't find the keyboard there for a second. So if you go to the functions key, miscellaneous, and do this log A, or you could do the underscore thing. Well, actually, it was log base 10. And you don't have to write that, but calculator, you just write the word log. It would be log base 10. So back here, log base 10 of 2 plus 7 is 7.301. And that wavy equal sign means approximately. All right, the next one is an exponential with not in the same base, so we want to isolate this. So first thing we'll do is add 5 to both sides. So e to the x over 3 is equal to 6. So you want to do log base e of 6 is equal to x over 3. Whoops, getting ahead of myself here. And then multiply both sides by 3. So log base e is the natural log. So 3 natural log is 6. So now I'll go into the calculator. So 3, there we go, functions, and then miscellaneous natural log is right here. 5.375. And we'll tell you on an assessment how many decimal places you want to do there. But so approximately 5.375. And then back here. For the logarithm equation, you want to isolate the log. So you want to get this log by itself. So first thing you're going to do is divide by 6. So log. And I'm going to write a 10 here because that will be helpful when we change it to an exponential. So here's my base, here's my exponent. So you're going to change this to 10 to the 6th. Equal x minus 2. And then you want to do add 2 to both sides. So you have 1 with 6 zeros. And if you add 2 to that, then it's this number here. 1,000,002. Or if I use my calculator, so 10 exponent 6, and then plus 2. So 1,000,002. All right, next slide. Can't have the same base again, so here we're going to subtract 1 first. Negative 2 natural log of x equal 4. And then divide by negative 2. And let's go ahead and write this out as log base e of x equal negative 2. So this would be e to the negative 2 equal x is the equivalent exponential, or 1 over e squared equal x. I take my calculator and I'm pretty sure if you just type the e, yeah, so if you just type e, it gives you the Euler number, and then exponent negative 2, or 1 over e squared is this number here, 0.1353. So 1353. So I could circle the decimal approximation and the exact answer. So if I did that for the previous problems, it would be like this here. And this one would be the exact answer and the approximate answer. And for this one, it would be, this is the exact and the approximate. So I would accept either unless the directions were to get the answer to the 3 or 4 decimal places. So here's the practice. So here you want to isolate 10 to the 3x, and then log base 10 of 9 equal 3x, and then divide by 3. So I don't have to write the 10 when it's base 10. That's the common log. So log 9 over 3. I'm not going to get the decimal approximation. You can do that on your own, but you can put this on the calculator to get the decimal approximation. I'm just going to leave it as exact answers on these examples here. So this one, you don't have the same base again. So you can change this to an exponential, the base exponent. So 4 squared equal x minus 3. Add 3 to both sides. And this one you don't have to put on the calculator. You get the exact answer of 19. This one, you divide by 8 here. So this one you could actually finish by getting the same base here. So 8 is 2 cubed. So negative 3x equal 3, and x is negative 1 then. So once again, you don't need a calculator for that one. Comes out to be a number answer, an exact answer. This is an exact answer, but if you put it on a calculator, you get a decimal approximation. And then this one here, notice that this has the same base here. So we're just going to equate other things next to the logs. So add 4, 20 equal 4x, and then divide by 4, and x is 5. This one doesn't have the same base. We can take the base 5. This is going to be the exponent. And then divide by 10. So 125 divided by 10 is 12.5. Not the same base, so I'm going to change it to a log form. Log base 10 is 70 equal x plus 2, and then subtract 2. And then you'd need the calculator to get the decimal approximation, and I'm not going to do that. You're going to do that on your own. And then this one, you want to isolate this here. You're going to subtract 10 from both sides first. And from here, I can get 16 as base 4. So x is 1. So some of these are a combination of not having the same base and then getting the same base. And then this last one has the same log, natural log, or log base e. So you're just going to equate the expressions next to the log. So subtract 2x. So 9 is 4x minus 7. Add 7. 16 equal 4x. Then divide by 4, so x is going to be 4. That doesn't check. Wait, something went wrong here. 2x plus 9. Subtract 2x. Add 7. If I plug a 4 in here, it's 8 plus 9 is 17. Yeah, like that works. I don't know why I didn't think it checked the first time, but if I plug in for x, I get 17 on both sides. So 8 plus 9 is 17. Over here, 24 minus 7 is 17. So that's the right answer. All right, that's it. I'm going to go ahead and stop the video here.